Our next speaker is Lonnie Thompson, who's a professor of earth sciences at The Ohio State University, and the title of his talk is Earth's Climate History from Glaciers and Ice Cores. Is your computer hooked up? Okay, great. So I'll give you the 25-minute warning. Sure.
Thank you very much, Michael. It's my pleasure to be able to speak to you this afternoon. I want to talk about what's happening to glaciers around the world and what we can tell from the ice core records of the rate at which this change is taking place. We work at very high elevations in mountain regions around the world, and this is one of our drill sites. Huascarán is the highest tropical mountain on the planet, but it has a very long history of the climate in that part of the world. I want to technician here, for some reason we don't advance. Yeah, I want to point out it's a team effort, and these are our team at Ohio State, graduate students and postdocs, as well as the funding agents that make this work possible. So I want to talk about glaciers as recorders of global climate change. We're going to give an example of how climate change in the past has impacted cultures in the Andes in Peru. I want to talk about glaciers as indicators of climate change. Evidence for a recent acceleration in the rate at which these glaciers are being lost, and evidence that some of these glaciers are now smaller than they have been in over 6,000 years. And I want to just point to what I consider to be our greatest challenges in the 21st century. First of all, if you go in the hall of the National Academy of Sciences, you'll see this curve of CO2. And we're now at 393 parts per million by volume. And this continues to rise each year. We have in the ice cores a very long history of how CO2 and methane and many other gases have varied. This record now goes back over 800,000 years. And you can see that there's a cycle in these gases. This is Milankovitch forcing, a 100,000-year cycle. And CO2 rises to 300 parts per million by volume during warm periods, and it drops to about 180, 200 parts per million by volume during cold periods when we have lots of glaciers on the planet. Currently, we are at a no analog situation when we look at the levels of CO2 in the atmosphere, and we're very concerned about where the projections are of where we'll be in less than 100 years. We talk more about CO2 rather than methane. Methane has a relatively short lifespan of the order of a decade, whereas CO2 can remain in the atmosphere for decades to millennia. And if you look at, even if we were able to get a handle on this issue and stop production tomorrow, CO2 would be around for a very long time, impacting the climate of this planet. So here's a projection. If you're out 100 years, you'd still have 33% of that CO2. If you're out 1,000 years, you still have about 20%. Of course, part of the drivers here is our population, and that is increased. And it's kind of hard to get a handle on these numbers, but we'll have 219,000 more people at supper tonight than we had last night on this planet. So these are huge impacts. And we often don't look at what it requires to feed those people. And here's just an indication of how much is needed. And if you look at back in the natural system, if you look here in the U.S., in the pre-exploitation time, there were only 60 to 80 million bison in the Great Plains. So these are huge impacts. And if you look at energy, certainly we can see that consumption, if you look from space at the Earth today. But it's amazing if you look at what the projections are in the next few decades. This is from General Electric, of what the world would look like. And of course, the question is, where is that energy coming from? and how is it going to impact the climate on this planet? Well, we look at glaciers, and we have these very long histories out of the polar regions, but we now have histories going back over 25,000 years in the tropics. So we can start looking at how the climate system has worked as recorded in ice. This photo was taken of the margin of the Quelccaya ice cap. You can see the annual layers because there's a very distinct wet and dry season. And the same place in 2002. So it kind of brings home the message that not only are we losing the glaciers, which are a very important water resource for many people, but we're also losing the history that's recorded in this ice. So ice records many parameters in the climate system, and I'm only going to mention two of them. Temperature as recorded in the isotopes of oxygen and hydrogen in the ice, and also the net accumulation, the amount of precipitation that falls through time. There are very few archives that allow us to look at that, and ice does. The analyses are done in clean rooms, the chemistry and the dust, isotope labs. We now have over 7,000 meters of core stored at minus 30 degrees C. It's the only tropical collection on Earth. And we design and build the drills to recover these cores. They have to be lightweight, portable systems. I was asked to say just a little bit of how that's done. So here's a typical drill setup at 20,000 feet. The power sources vary. We developed the first photovoltaic-driven ice core drill back in 1983. A wonderful source at 20,000 feet. They perform 20 to 30% above manufacturer specs. But we also have redesigned diesel engines to be more efficient and actually work in cold environments at 20,000 feet. Transport is a problem. We're above most aircraft capabilities, and therefore we use what's available in the different parts of the world. This is a view of the Quelccaya ice cap in the Andes of Peru. It's the largest tropical ice cap on our planet. If you're working in Tibet, you have to move across the Tibetan plateau and then up to the top of the Himalayas. And getting the ice out of those areas requires a combination of using Sherpas to get down to the edge of the ice. But when you get to the edge of the ice, you're still 3,000 or 4,000 feet above the plane where the vehicles are. So you have to use the local transport system. And in the Himalayas, that's yaks. Those are insulated boxes. There are 6 meters of core in each box, 12 meters per yak. We drill 500 to 600 meters of core. So you have to have a whole herd of yaks to move that down to the trucks and then eventually air cargo it out of China. So there's a lot of logistics that go in to get the records. So we have drilled around the world. These are the places that we've recovered records. And the tropics are a very important part of our planet. Over 50% of the surface area lies between 30 degrees north and 30 degrees south. The central panel here shows sea surface temperatures. And you can see that if you look at the lower panel, that sea surface temperatures drive precipitation in this part of the world. But if you get up to 500 millibar level, where the glaciers are, temperatures are very uniform in tropics, and they're all behaving in the same way. So I'm going to take you to one of these, the Quelccaya ice cap. It's 14 degrees south of the equator in the Andes of Peru. This shows the location right above the Amazon basin. It's in an area where you can see the monthly precipitation, very distinct wet and dry season. If you look down a crevasse, you can actually see every dry season, every one of those bands. And if you go down in the crevasse, you can see how uniform these bands are. So by measuring the thickness of those, you can get the net balance precipitation of the past. So you drill through 168 meters and bring that core back. You analyze it. And here's just one section to show you how the isotopes show us the annual variations, as well as the dust. Measure the thickness, and you got the precipitation. Now, if you bring those back and you analyze them, then you can look at, in this case, we're looking at the last 1,000 years, decadal averages of isotopes, which is our temperature proxy. The reds are warm periods, the blues are colder. So you can see the cold during the Little Ice Age. You can also see the warming in the 20th century. But you can also see the reproducibility in these records. The first one was drilled in 1983. When we couldn't bring back frozen ice, we didn't have the technology. We brought back 6,000 bottled water samples. And 20 years later, when we brought back frozen core, you can see the reproducibility in that record. You can look at the precipitation over the last 1,000 years. The browns are periods of reduced precipitation, and the blues are heavier precipitation. And so you can look at the 20th century and see the warming, and you can also see that it's been wetter than average. Now, this area of the world has a very long history of human occupation, and so understanding how that climate varies through time becomes very important. If you look at the isotopes in these cores and compare them to sea surface temperatures, you can see there's a very high correlation to temperatures in the central Pacific Ocean. And if you look at this annually back to the period for which we have sea surface temperature measurements, back to about 1857, you can see how correlated the isotopes in these cores and the SSTs are. So you can use the ice cores to actually project those back into the past. Peru is also impacted greatly by El Niños. This is the 97-98 El Niño, very wet in the north, northern Peru and Ecuador, but very dry in the south where this ice cap is located. This area has this very long history of pre-Spanish occupation and cultures like the Incas. And we can work with archaeologists and anthropologists and actually look at how climate has impacted those cultures in the past. So I'm going to take you very quickly through the last 1,800 years. And if you look at these cultures, when it's dry up in the southern Andes where this ice cap is located, we have development of coastal cultures, and the capitals are in the coast. When it gets wetter, as you can see in the blue here, the cultures move inland, and the capitals move inland. When it dries again, they move back to the coast, and the capitals move to the coast. And when it became wet again, we had the rise of the Inca Empire, which lasted until the arrival of the Spanish in 1531. Now, if you come to the 20th century and you look, the ice core record would say people should be moving inland. But we know that since about 1947, people have been migrating to the coastal deserts of Peru, to the big cities like Lima, in search for a better way of life. And now there's tremendous water shortages, and they're looking to put in tunnels through the Andes to capture water that now goes into the Amazon and bring it back. But in the long history of humans, you would be moving. So we can take these records and we can combine them and we can look at the long-term history. This is isotope records for the last 2,000 years. You can see the Little Ice Age, you can see the warming in the 20th century. We can compare that to other temperature reconstructions for our planet. And you can see the similarities in these curves. And the red curve here is our actual instrumental record. And so the real unusual period is the last 50 years in these records. So the changes are very abrupt. And you can see it in the ice. The upper photo shows the margin of the Quelccaya in 1977. That whole area is now a lake. And the bottom photo shows the margin of that lake, the backside, in 2002. And right at the base, you can see a man walking there if you look closely. The cliff is 30 meters high. We found a wetland plant deposit, perfectly preserved. And this plant could be identified and dated. And it shows us that this ice cap hasn't been smaller in 5,200 years. Otherwise, this plant would have decayed had it been exposed. In the insert photo there, you can see the plant, you can see where the ice wall is in 2002. 3 years later, in 2005, you can see the plant is in the forefront where the ice pick is, and you can see how much the wall has retreated. We've now collected over 60 plants that have been exposed as this wall retreats. And most recently, in 2011, we collected plants on the other side of this lake, which formed about 35 years ago. And those plants date 6,300 years in age. And so if you look at the age of the plants on both sides of this lake, you can see that 6,000 years ago, it took 1,600 years for this glacier to advance to capture those plants in the forefront. But it only took 35 years to retreat in recent times to re-expose those plants. So they're changing very abruptly. We can look at the longer records coming from glaciers like Huascaran to the north, look at the isotope record, look at the present, and project that back in time. And if you do so, you can see you come to a place where temperatures were similar to today, and that's when these plants were growing around this ice cap. The real difference is how rapid the recent changes have been. Nature's best thermometer, perhaps its most sensitive and unambiguous indicator of climate change is ice. And I like this quote from Henry Pollack, "A world without ice. Ice asks no questions, presents no arguments, reads no newspapers, listens to no debates. It is not burdened with any ideology, and it carries no political baggage. As it changes from a solid to a liquid, it just melts." So if you go around the world and you look at what's happening to the glaciers, up in Alaska, if you're up in the Brooks Range, 100% of the glaciers are retreating in today's world. In the southeast Alaska, where the Muir Glacier is located, 98% of the glaciers are retreating. If you go to the Himalayas, it's very hard to find old photos, but here's one of a glacier taken back in 1921 and what it looked like in 2009. And when you look at these pictures, ice is just water on land. When it melts, it goes in the world's oceans and contributes to sea level rise. Over in the Alps, a photo from 1903, a recent photo in 2005, 99% of the glaciers are retreating in the Alps. If you go to the tropics and you look at what's happening ice in that part of the world, this margin of the Quelccaya ice cap, the largest outlet glacier is Korikalis, a photo in 1978, and a photo taken in 2009. This lake actually started forming in 1991, now covers 84 acres, it's over 60 meters deep. 100% of the glaciers in the tropics are retreating in today's world. If you go to the Himalayas, a very important part of the world, covers over 5 million square kilometers, one of the largest glacier stores of fresh water, some 46,000 glaciers. Most of them haven't been studied. And if you look at the source of the major rivers in that part of the world, the Indus, the Ganges, the Brahmaputra, they source up in the Himalayas. And therefore, what happens to those glaciers will have an impact on people, and particularly during the dry season. I'm going to take you very quickly to one of these, Nanunami, which is the headwater of the Indus and the Ganges and the Brahmaputra River. This is what the mountain looks like, and if you make your way up this mountain to the summit, you'll find a very large ice field. And we drilled 3 cores to bedrock here, and you can see that they're up to 158 meters deep. And the first thing you do when you bring the cores back is you look for radioactive bomb horizons. All the thermonuclear tests we've done in the atmosphere have left a radiation level. So the first one we look for is the 62-63 Soviet test, and you can see in all the previous cores drilled in that part of the world, it's there. But you don't see it on Nanunami. Then we look for the Ivy test from 1952 to 1958, further back in time. We find that in chlorine-36 preserved in ice around the world. But you don't find it on Nanunami. You don't find it because that glacier is melting from the top down. It's no longer accumulating in today's world. And so this has tremendous implications for water resources on that area. Working with the Institute of Tibetan Plateau in Beijing, China, we have looked at 7,090 of those 46,000 glaciers from satellite images from 1970 to the present. And this actually shows the percent of ice loss per year. So the bigger the dot, the greater the loss of ice. And you can see it's not uniform across the plateau. We're losing more ice in the south along the Himalayas than in other parts of that region. You go to Africa, to Kilimanjaro. The oldest photo is shown up in 1912, and you can see what it looked like in 2006 at the bottom there. The first map was made in 1912, and we've continued to map the loss of ice in that part of the world. So we've lost about 85% of the ice on the mountains since 1912, 26% since the year 2000 when we drilled there. So the loss of ice is accelerating. And again, we put ablation stakes on these glaciers. And you can see when it was put out in 2000, and another view of the same stake in 2004. These glaciers are no longer accumulating. They're wasting from the top down. And so that has, again, tremendous implications on water resources. So if you look at the glaciers on Kilimanjaro and you look at the volume of water or ice loss, and you look at what percentage is coming from shrinking, the aerial changes, and that's what you see when you observe glaciers from satellites, and the percentage coming from thinning, which is the changes in thickness, then you can see that they're about equal. So we miss that when we look at satellite images. Here's a view of the crater on Kilimanjaro, the Furtwängler Glacier in the foreground in 1999, the same place about 6 months ago. So you can see how rapidly these glaciers are thinning and also breaking up. So those glaciers will disappear in the near future. The last place I want to look at is over in Papua, Indonesia. This is the only glacier that exists between the Himalayas and the Andes in South America. If you look at the photos in this area, the oldest photo we found is 1936, and you come forward in time, you can see how the ice is being lost. These are Landsat 5 images, the upper one in 1989. The blue areas are glaciers. Many of those glaciers had disappeared by 2009. This is the only glacier we've ever drilled where it rained every day while we were at the drill site. And you can see in the lower photo that that's where a tent set for 2 weeks. In 2 weeks, the surface lowered 30 centimeters. If that's any indication at the rate the ice is being lost, that comes out to more than 7 meters of thickness per year. And we drilled 3 cores, 2 to bedrock. It's only 32 meters thick. So if you do the calculations, these glaciers are going to be gone in a matter of years. And the history that's recorded in the ice. Here we compare the loss of ice on Kilimanjaro, the red squares, with that on the New Guinea glaciers. And you can see they're very similar. And if you project those into the future, you can see the glaciers are going to be gone in the next few years at these sites. So there are tremendous implications for people who live in those areas. If you look at what might be driving that, if you look at the Intergovernmental Panel on Climate Change projections, with an 800 part per million increase in CO2, you can see that there's a vertical amplification in the low latitudes. And you can see the elevation of these drill sites. And they are very sensitive to these changes, and we believe these glaciers are already responding to those changes. So if you were to look at the Earth as a whole, where we have glaciers and where we have observations of ice, the ice is disappearing very rapidly. Sea level is rising currently at about 3.3 millimeters per year, but that's projected to increase as we go forward in time. So climatologically, we are in unfamiliar territory, and the world's ice cover is responding very dramatically to these changes. So if you were to look at what are our greatest challenges in the 21st century, I would say that it's learning how to get along with each other. This is an issue that's been with us for a very long time, and you can debate how well we're doing that. But the other is learning how to get along with the planet that we live on. Where is that power going to come from? Certainly the consumption on the planet is growing much faster than the population, and it takes energy to do that. And so I think this whole question is key. It's very key to what the climate will be as we look forward in the future. These two challenges deal with human behavior, and they are therefore very closely related. And so I think that when we talk about solutions or how do we really need to have a better understanding about people and how we react and how do we change. So I want to close with this photograph of the Earth. We saw this earlier, and certainly if you were to look at the planet from space, and as Dr. Chu was saying, it's a unique place. We know that. And if we talk about global climate change, if it's for sure that nature's the timekeeper on this change. And unfortunately, none of us can see the clock that we're working with. But we have a good idea that it's ticking. And so I think these are extremely important issues, and I think this is a tremendous session to have here at APS. So thank you very much.
Thank you. I'm gonna stand down here so I can see people, and then I'll. So we have time for a couple of questions, and I'm going to stand down here so I can actually see your hands this time. Over there. And if you can make your way to a microphone, that would be very helpful.
Yeah, I sort of saw some of it.
Oh.
I saw some of this in your graph, but maybe you could say a few words on where are we now versus the 100,000 ice age cycles, and what kind of temperature range that was versus what we've seen so far in human-made.
Well, if you look at the normal glacial interglacial cycle, this is determined by Milankovitch forcings, and they include eccentricity, this 100,000-year cycle, which has to do with the fact that our orbit is not a circle but an ellipse around the sun. It's also driven by the fact that we are tilted on our axis, and that tilt changes from 22.4 degrees up to 24.5 degrees, and we're currently at about 23.5 degrees. And we also have the fact that we're wobbling on that axis, and that creates a 22,000-year precession cycle. And so those kind of combine to cause the changes that we see in our climate. If you look at that combination, you really actually have to go back to isotope stage 11, which is about 415,000 years ago, to find an interglacial very similar to the one we're in now. That interglacial lasted 30,000 years. And ours is different because we're outside of that natural forcing. On top of that, we now have the human component. And so a lot of people look at this interglacial will actually be a super interglacial when we look at the long-term history.
We have a question over here.
Yes. There are, from the talks I've seen today so far, and also from what I've been reading over the past 8 years or so, there are a number of processes involved that one has to take into account regarding climate change, such as the Pacific Decadal Oscillation, which was in its cool phase when people were worried about global cooling from around 40s to the 70s. I think the best thing that one can have, just general, is for the American Physical Society to promote an interchange between people who have the different opinions on climate change. So when I was the chair of the New England section of the American Physical Society, we had a session where we had people from both sides of the issues, whether humans are causing climate change or whether they're not. It's a problem, I think, and what one needs is more of an interchange. And what's happened is that the American Physical Society has come out with an incontrovertibility stand about climate change, and this has been resulting in a number of people who've resigned and who have challenged the APS. So in particular, one of the groups on climate physics, one of the organizers of the group just resigned, and I can pass out something which gives people an idea of what the problem is. So what I'm appealing to is the APS to have a more balanced presentation of what's going on with the issue of climate. I'm not saying that glaciers aren't melting in part because of that. So I will just pass out something, and if you can read it if you like. Thank you.
Okay, thank you very much. So you don't need to respond to that question. I'll respond and just say that what the APS has decided to do by forming this topical group on the physics of climate is to concentrate on ways that physicists can contribute to our understanding of climate and climate change. And so we have time for one last question, assuming that it's a question for the speaker and not a statement. So do you have a question for the speaker?
I have a question for the speaker.
Okay, please ask the speaker a question.
This is out of my own ignorance. You said that methane has a lifetime of something like 10 years in the atmosphere. What's causing it to decay?
It's converted to CO2. It's pulled out by precipitation on the Earth, converted to CO2. So it doesn't have this the long residence time that we find with carbon dioxide.
Is it photo? Is the sun causing it, or is it just somehow the general the way the atmosphere moves around?
It's a process of precipitation, a lot of different processes on the Earth, and the conversion to CO2 by those processes.
So the implication is we have less to worry about unless we have massive methane leaks, or we really have to worry about CO2.
Well, CO2, methane has a huge impact as a greenhouse gas. It's just that its residence time and its impact on the system will be not as long-lived as what we find with CO2.
Thank you.
Thank you. So one very quick, and I assume it's a question, right?
It's a question.
Good.
You mentioned that CO2 has a decay time of hundreds to thousands of years. So a couple of things. First, is the present level of CO2 and what's happening with glaciers melting, do you consider this dangerous? And if we were to, even stop at this level, which we're not going to be able to probably, but what can we do about it if it's going to last for hundreds of years?
Well, I think these are issues that certainly we need to think deeply about. But the fact is, in the climate system, there is a 20 to 30 year response time. It takes, before we see the full impact of what we've already done to the atmosphere, it's going to take that long. So this is not something that you change quickly. And so if you were to look at the future, I would say that we are really looking, there was a time when we talked about preventing climate change, but I think where we can mitigate climate change, we can look at ways to capture CO2, sequester CO2, reduce the emissions of CO2 by looking at different energy sources. We can talk about geoengineering, ways that you might be able to come up with ways to counter what we see happening. But that, of course, is very dangerous. We have to look at adaptation, because we're going to have to adapt to what is already underway. And this may impact our agricultural practices, where people choose to build. We saw the losses insurance companies are facing. Insurance companies are already seeing the impacts of these natural disasters in the climate system. So, and the way companies work, of course, is they move out of those areas where the risks are too high, because companies are in the business of making money, but that leaves taxpayers and other people to pick up those costs. And I think what we don't do with mitigation and adaptation will lead to suffering. And many of the places where I work, the people who live in those areas are already being impacted by the loss of water resources as these glaciers disappear.
Thank you very much, Lonnie, for sharing with us your beautiful data on glaciers and ice cores.
Thank you.